Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Securing Flash Memory in IoT and Edge Devices, brought to you by Tech Online, Macronics, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many of your questions as we possibly can at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers, and at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation, Securing Flash Memory in IoT and Edge Devices. Discussing today's topic are Jim Yastik, Technical Marketing Manager, Macronics America. Jim is responsible for ecosystem market, product, and business development at Macronics America. And with 30 years of experience in the high technology sector, his previous roles include engineering, product marketing management, and business development for organizations focused on the semiconductor, communications, and embedded software markets. And joining Jim today is Chris Jones, Principal IoT Security Specialist, Quantique Limited. Chris Jones is Quantique's Principal IoT Security Specialist, and following a 28-year career in project management and field applications engineering, Chris spent 2 years as a senior application engineer at Secure Things Incorporated in Cambridge, UK, working in IoT security. It's with great pleasure I now turn this special session over to Jim to begin. Jim, take it away.
Thank you, Chris, and hello, everyone. Welcome to our webinar where we will be talking about the latest IoT, IIoT trends as it relates to how memory security is being implemented to support these new architectures. Chris is my co-speaker from Quantique. Quantique is a quantum-driven cybersecurity company addressing the growing challenges of end-to-end IoT security. They use the most advanced technologies and techniques in cryptography and quantum physics to deliver unforgeable identity key derivation technology using quantum tunneling, while delivering both certificate and key lifecycle management. Quantique is redefining the concept of security for IoT by creating a seamless bridge between the silicon, device, and cloud platform worlds. And then we'll finish up by going deeper into the use cases for Secure Flash, what data is being stored, what features are being added to protect end products, and then finishing up with an example of where Secure Flash is successfully being used. First, I'd like to start by saying that Macronics has been serving the industrial and data center markets for many years now, and our business continues to grow due to our inherent strengths. We own our own fabs, so it gives us the ability to control our quality levels that allows us to speak in terms of parts per billion defect rates now. And for the same reason, we can control our longevity, which is also important, particularly in industrial applications. Modern society is currently experiencing exponential growth of connected devices on public IP networks. Just recently, IoT Analytics, a well-known IoT market research firm, expected the global number of connected IoT devices to grow 9% to 12.3 billion active endpoints in 2021. They expect that to grow to 27 billion by 2025. And these numbers don't even include smartphone, tablets, laptops, and that sort of thing. The range of targeted IoT devices could be anything that senses, processes the collected data, and then sending upstream to the cloud. And I'm going to get into some example applications later. There are many forms of attacks that could be carried out on these devices. To just give one common example is the use of botnets to carry out DDoS or distributed denial of service attacks. The effects of this threat alone have been enormous in disabling major websites in the past. And as more vehicles, devices, homes, and things become connected, the threat of attacks is inevitable. And so the challenge of protecting valuable assets from theft or maliciousness has forced many organizations to devise more secure system architectures. And to name some of the reasons why we're seeing enormous growth specifically is because so much data is being produced that the network architectures are migrating closer to the sensors, either to the premise edge or to the sensor themselves. So store, process, and forward use cases are growing across all industries, driving a need for more memory storage. Then there's the affordability of high-performance compute and sensor technologies. There's the growth of communication networks driving availability of internet connectivity. A good example of this would be the continued growth of 5G networks. There's the availability of large-scale data management providers like Amazon AWS, Microsoft Azure, Google Cloud, and they're driving new security requirements. There are increasing requirements to meet privacy regulations like GDPR. Then there's need to secure data and protect networks as a national security requirement. There's a need to thwart internet attacks. There's an increase in remote content availability, and that needs to be protected against unauthorized use. Then there's the growth of buildings and vehicles being protected with biometric keys for authorized entry and monitoring for unauthorized entry. This is increasing the amount of highly secure memory that's needed. And then finally, there's corporate theft and increasing the threat of reverse engineering designs to create cheaper knockoffs. So I'd like to talk about the overall infrastructure that is IoT, or really what is increasingly being termed as the Internet of Everything, or IoE, because the need for security crosses all the domains that are involved, from the public cloud down to the end node. It really requires compartmentalizing security in different operational domains in the system to avoid class attacks or wider breaches when the security holes are found. So having a comprehensive interlinked security system that works well together is critical. We were trying to come up with a graphic that captures what an overall IoT system would look like, and I came across this graphic from a white paper called The Introduction to Edge Computing in IIoT from the Industrial Internet Consortium. I think it does a great job of helping to visually explain all aspects of what an IoT system looks like and what's possible. So we decided to go ahead and use it and give credit to it. But what you can see here are the cross-cutting functions that help drive different layers in the system, from distributed data management, making sure that the right data is stored at different layers, and that it bubbles up to analytic dashboards, so accurate conclusions are developed and correct decisions are being made. And that can't be accomplished without a link to what is being done or seen and analyzed at different domains, like a feedback loop. And then there is the global orchestration, or the management of the system, to make sure that it operates efficiently and correctly. Then finally, making sure that communication connections in unsecure environments are being done as quickly and securely as possible. This also includes the aggregation of traffic from different end nodes and client-side edge devices. And all of this, as I stated before, needs to be done securely. There are a wide range of applications that fall under IoT or IIoT that need to be secure. I show some of them here, but basically it's any application across a number of markets that senses something, processes what it sees, and then reports it back to a server. I mean, there are many examples in industrial, such as industrial automation. Some examples would be, real-time crop monitoring, IoT analytics in agriculture, livestock management, smart greenhouses, smart waste management, and that sort of thing. And then there's industrial control that includes smart robotics, preventative maintenance, remote production control, asset tracking. And then, we hear a lot about smart cities. I think some good implemented examples include traffic management, flood control monitoring, video surveillance, and streetcar maintenance. And then there's significant changes happening in healthcare. One of the biggest trends is medical remote device applications that continue to grow as doctors and nurses monitor their patients remotely. And then there's similar increases in telemedicine. And then automotive shipping, vehicles are being designed that connect to the internet, and there's that's growing rapidly and being implemented with autonomous features. And then there are premium content authentication, electronic payment, user authentication for authorized entry and use, as well as maintenance authentication that's required. And all of this is stored in secure flash. And then there's logistics and operation support needing to be secure for shipping industries. And then lastly, energy. Protecting the energy grid has been an important topic for some time and is a national security issue for any country. So what kind of specific data are required to be securely stored, and what are the use cases? Here I outline some of the use cases for advanced secure memory. There's the storage of highly sensitive information such as keys, credentials, certificates, DRM or digital right management. There's content service keys, for example, audio video streaming, secure logs, and other PII or personally identifiable information like biometrics, passwords, contacts, etc. There are designs that require secure data memory and memory for code storage, so you can combine the two in a dual-use memory device. Then there are older designs that need to be upgraded for security reasons without changing the microprocessor or microcontroller, or microprocessors that don't even have secure embedded flash. And then you've got designs that utilize a secure element that can be combined with a non-volatile memory, and that lowers BOM costs, but from a security standpoint could validate secure boot and remote firmware updates in the flash device itself, keeping software and other transactions to a bare minimum on the bus. Then there is memory supporting OS architectures that have multiple users, such as multi-tenancy and hypervisors that require multiple sets of credentials. Then there's support for secure provisioning in unsecure manufacturing environments, and again, reprovisioning in the field. Then there's protection of firmware rollbacks and cloning. Then you've got memory devices that are protected against host device eavesdropping and memory device tampering. And then finally, support for root of trust requirements through unique ID, authentication, and encrypted links. Now, at this point, I'd like to hand the presentation off to Chris at Quantique to further discuss IoT security issues. Chris, over to you.
Hey Jim, thanks very much for that. Hi everybody, my name is Chris Jones. I'm the Principal Security Solutions Specialist here at Quantique. What I'd like to do today is show you some of the important things that you must consider when looking at adding security to your connected product. So let's go ahead and have a look at some of the things that I believe are important for you to consider. So here at Quantique, we produce products that bridge the IoT security scaling gap. Well, what does that actually mean? Well, basically, as the growth in deploying connected devices continues at a pace, the manual approach to deploying, managing, and maintaining secure devices simply becomes impractical. If you consider looking at installing temperature sensors throughout a building, deploying those sensors then and connecting them to some kind of security service can be a long process. A recent study by Kaiser Associates commented that onboarding of devices can take, on average, up to 20 minutes per device. Now, many devices can be deployed at remote, far-flung locations where technicians and employees often are just not in attendance. So for successful IoT scalability, network and device management can't be seen as an afterthought. It must be considered up front and planned from the outset of developing your connected product. Let's start out by looking at the key objectives of security. What is it that we are actually trying to do when we talk about security? So let's start by looking at device and data security. As we will see later, a key feature of security is authentication. This is where a device is able to prove its identity, which leads to trust. An example of this in the real world is at an airport and you show somebody your passport. The officer would look through your passport, check the photograph, and he can see you and therefore has a good indication that you're the owner of the passport. In the digital world, that's very difficult. The digital device may be very remote and can only send certain information. So how can it actually prove itself? So we'll investigate that. Then there's the confidentiality of data. So we want to be able to hide our data from outsiders. The data may contain personal information, intellectual property that we really want to protect. Another important factor is that we want to check the integrity of our data. So this means that if we are sending data from one party to another, we want to make sure that during the transfer of our data, it wasn't corrupted or modified by a third party or what we say a bad actor. Security needs to be continuous during the life cycle of your product as well. So software updates are a key security requirement, ensuring that vulnerabilities are removed from software. The authenticity of software, again, must be assured. It may need to be encrypted and certainly transmitted over a secure channel. Data monitoring is also a popular security tool that checks for any anomalous behavior in the data from an entity signifying that the connected device may have actually been compromised. Now, certificates, they are used to create trust between connected devices. They are a tool for transferring cryptographic keys between entities. They can be used to manage devices by revoking certificates and isolating devices. We'll cover these in some details a little bit later on in the presentation. We're seeing an increase in legislation due to the rapid growth in connected devices. Governments and organizations are actually getting together to try to produce security by design best practices and guidelines for companies to assist them in the development of their products. Legislation is forcing companies to design security into their products, which help to build trust in their products by their customers. With improved security comes better performance. It ensures that your product stays connected for longer. Denial of service attacks can be dramatically reduced, ensuring the availability of your product to your end customers. Let's now look at some of the key components of security, the things that are very important and that you need to consider when you're developing a connected product. The first thing is the early adoption of security. Security is not something that you can simply bolt onto your product. You need to think about it in the very earliest parts of your design. We recommend that you implement a security by design approach and do this at the very earliest stages of the development of your product. Even during the design of early prototypes, you should include security functions. This may be painful when you're focused on core functions of your product, but it will pay off. Implement security design guidelines and good practices throughout the design of your product. These are available from many public organizations. Some good sources are the IoT Security Foundations and ENISA. They are very good and extensive documents to help you develop good practices. We also recommend that you carry out a security risk analysis. Now, this does sound like a lot of work, but it's not necessarily so. You can simply start by gathering the relevant development engineers into a room and discuss things like possible threats to your product, what vulnerabilities it actually has and the probability of their occurrence. Discuss the possible impacts of attacks. You'll find this is very useful, and a lot of things that you may not have considered prior come to the fore. An example would be a streetlight controller that sits on top of a streetlight, for instance. It is not likely that somebody is going to climb up the pole and to try and get access to the hardware when they may simply be able to access the network the controller is actually connected to. They may be able to access the information using a computer from the warmth of their home. This may lead to less design effort being spent on the protection of the hardware controller and maybe more on the security of the wired or wireless connection to the controller of the network. This also leads to the consideration of the information under the control of the controller. Does it contain personal information that could lead to identity theft? Does the device contain cryptographic keys that could compromise the entire network and give access to other more valuable assets? These are the kinds of things that come out when you have a risk analysis discussion. So what are the benefits of early adoption? The benefit of early adoption is that you avoid bolt-on security. This classically leads to vulnerabilities due to the design having not been thought through correctly. The other benefit is that you establish a security culture within your company from the very early stages. If engineers are thinking about security all the time, for instance, it comes up in meetings and it's covered in design reviews, then the culture ensures that security is being discussed during the whole development of the project, leading to the end product having much better security. Okay, so adoption is part of the process of security. So what about actual components of security? One of these, which is very important, is the unique device identity. We cannot overstress how important a device having its own unique identity is. It is the root of trust from which many other aspects of security are derived. So what do we actually mean by identity? We do know that microcontrollers have identities or IDs that are embedded in the silicon during manufacture, but these are not a true identity. They're not necessarily unique. What we mean by identity is that it must have a unique random number, and this number must be able to be cryptographically proven. This is going back to the passport idea. We need to be able to prove that we have this identity. The identity must be based on a cryptographic function. Typically, you tend to use an asymmetric cryptographic key pair. The identity can then be proven by the fact that the device owns the private part of the public-private key pair. Since it is cryptographically based, the unique identity is based on a number that is random in nature. That is, it has a very high entropy. We cannot base a unique identity on a serial number baked into a microcontroller OTP register. The benefits of a unique identity that is cryptographically based is that the device can be authenticated when it comes online. The authentication of a device leads to trust, which provides many other benefits, such as secure communications with the device through encryption, and that a public key infrastructure can be implemented, which will be covered later. The next important component I'd like to cover is the root of trust. So what is a root of trust? This could be described as a set of implicitly trusted functions that the rest of the system or device can use to ensure security. The root of trust is the foundation on which the device maker can build a tower of trust, or sometimes called a chain of trust. So let's examine some requirements of the root of trust. A root of trust must have an immutable boot path that cannot be interrupted by any external interference. So what does this mean? So in the case of a microcontroller, this would mean that during booting you can't stop the process by maybe using some kind of hardware interface, such as a debug port or a JTAG interface, to stop the processing of the boot and therefore gain access to the device. Typically, a secure device has these ports disabled, which means nothing can disturb the booting process. That's a typical feature of a secure microcontroller. The next requirement is for the root of trust to have the ability to ensure a secure boot process that actually authenticates the application software prior to jumping into the main application. So the process requires that the software digital signature is verified, thus ensuring that the device can trust the software, since it has been confirmed it originated from a known and trusted source, i.e. the owner. Next is the ability to program and lock sections of memory so that they're immutable. This is used in the case where you want to store trust anchors in the form of digital certificates. These items are used to authenticate software. They are typically programmed into the device as part of its provisioning step, which we'll talk about a little bit more later on. Finally, the root of trust can increase security by supporting a security storage facility which prevents the access to cryptographic keys from an unauthorized user. So a typical example of this is ARM's Trust Zone, which is a hardware secure barrier between the trusted and untrusted zones of the microcontroller. The technology creates a trusted execution environment that can be used to store cryptographic keys that can be utilized by the main application, but of course never exposed. Previously, we briefly mentioned public key infrastructure. So what is a public key infrastructure? So this was actually originally developed by GCHQ in the 70s. So GCHQ is the UK government communications headquarters. The technology is basically a set of hardware, software, people, policies and procedures that are needed to create and manage digital certificates. And a digital certificate, well, which it also sometimes is known as a public key certificate, is used to cryptographically link the ownership of a cryptographic public key with the actual identity that owns it. Digital certificates are created and signed by trusted certificate authorities. So these are companies that verify the organization that owns a certificate against the information that's included in the details of the certificate. So things like the company name, their website URL, their location, and other important information. Once a certificate authority has verified the ownership and signed a certificate, you can be confident that the information and the public key on that certificate can be trusted. And with trust, you can then utilize digital certificates to authenticate data, encrypt data using cryptographic keys, and prove identity. A practical example of the use of public key infrastructure is that you can set up secure communications between two entities using the public keys that are included in certificates. Transport Layer Security, or TLS, is a good example of this. You can also use it to secure software updates to connected devices. The PKI basically provides a chain of trust using these digital certificates, which ensures that any software updates that have been delivered can be authenticated, all the way back to the certificate authority, and therefore the owner of the certificate. Also, the PKI allows you to manage your connected device over its entire lifetime by the use of certificates. Use the certificates for renewal and revocation. These are some of the processes that are implemented with certificates. So we've mentioned identity a lot so far. So why is it important? Why is this the fundamental basis of all security? Well, unique and provable device identity supports other important functions that you need in a secure IoT ecosystem. And here are four main requirements in a security system that are enabled through strong identity. So first is trust. And we talked about trust a lot in this presentation. And it's really important that a device is able to trust other devices. To do that, a device must authenticate itself before trust can be established. Once trust is established, then secure communications can be set up between the two entities. Then there is privacy. With identity, you can ensure that personal sensitive data and financial information can be kept safe and secure because you have a strong identity, and therefore you can set up secure communications and can transmit encrypted information securely and ensure that it remains private. Then there's safety. If you have strong identity, you can prevent malicious attacks in industrial and medical environments, and this is important where you do not want to put customers or end users at risk. And then the final one is integrity. This applies to both the device itself and the actual data being transmitted within the IoT ecosystem. A strong identity ensures that device software and firmware are legitimate. Now what I'd like to do is pass back over to Jim. He wants to talk to you about flash memories in a little bit more detail. Over to you, Jim.
Thanks, Chris. So if you compare different flash types, you've got embedded flash, external SPI flash, and secure flash. And as you can see, there are different attributes associated with each one. If you look at the interface for embedded flash, that's going to be a very large parallel bus that is on chip. And with external SPI flash, you get a standard SPI interface. And then with secure flash, the same is true, particularly with our Armor flash. And densities for embedded flash are pretty limited. So once the embedded flash is designed in, it's pretty difficult to change the density. With external SPI flash, obviously, you can just change out discrete devices and by changing the density. And the same is true for secure flash. And then embedded flash offers very strong security, and so does secure flash, like our Armor flash. However, external SPI flash typically is pretty weak in terms of security. It's always assumed that the details of the cryptographic algorithms are well known by an attacker, so it's only the secrecy of the key that ultimately provides the security. Trying to keep keys secret is one of the toughest challenges in deploying security. Besides the keys, other user-sensitive or private data are usually stored in the same security level as cryptographic keys. In some secure execution environments, a dedicated secure storage is required not only for secret key information, but also for application-specific data. Also, modern operating system architectures that support virtualization or multi-tenancy, it's a requirement to store and support the security credentials of multiple users for multiple applications. For complex systems, this secret information will be stored in external secure flash memories due to the storage size requirements. So the slide here shows a wide range of standard security features that are common in non-volatile memory being offered in the market. They're effective in protecting various threats to its contents. So why would a product need to implement memory with advanced security features? To start with, there's an overabundance of existing designs based on older microprocessors. So if there's a requirement to make the product more secure, it's expensive to do major redesigns of existing products, particularly with complex applications in a hard real-time environment that has been field proven. If a requirement has come from an organization's marketing department that it must now be connected to an open network, where will the required keys and credentials be securely stored to support secure access? On-chip embedded non-volatile flash memory, it's considered relatively safe if tamper resistance has been implemented. But increasingly, general processors suppliers, they're shrinking the embedded non-volatile memory footprint to only store phase 1 boot code, because as the technology nodes shrink from say 55 nanometers to 28 nanometers, the footprint for embedded flash is much larger compared to the CMOS-based processor and other peripheral logic that has to be shrunk. This is because embedded flash doesn't scale like CMOS-based logic. So 28 nanometers is about the current stopping point. And so expected overall die size and cost reductions fall short. Also, customers have varying density requirements, so betting on any given customer's memory footprint requirements is risky, and the embedded flash adds cost to the product that could be shifted to the customer. There are 3 major advanced security memory products available today, and that Macronics also offers: RPMC, authenticated flash, and a fuller featured secure flash. RPMC is a memory device whose main purpose is to provide sequencing information for signing digital signatures, and also to provide non-volatile monotonic counters for the host to support sequence frames in secure communication protocols like TLS, SSL, to thwart man-in-the-middle attacks. Several memory providers currently offer this type of flash as a dual-purpose memory. This means that there's a region in flash memory reserved for RPMC functionality, with the rest reserved for normal NOR flash. Authenticated flash devices also perform authentication with the host before a secure operation. A good example of this would be the RPMB feature in the Macronics eMMC product. Full-featured secure flash devices perform authentication and encryption along with a full range of additional security features. A good example of a secure flash with advanced security features is the Macronics Armor Flash product. It is a NOR flash device and has many of the standard security features listed on the previous page, as well as advanced security features listed on this slide. At this point, I'd like to introduce you to Macronics Armor Flash. I'm going to use it as an example of what a secure flash looks like. It is auto-grade and so AEC Q100 qualified. It's offered in temperature grades required in heat-intensive environments, meets longevity requirements of greater than 10 years, and has security certifications. In particular, our Armor One product has PSA certified level 1 device level qualification, which enables us to show our customers that we've considered a baseline of security. Armor 2 is CAV-P validated and FIPS level 2 ready. It has a range of secure features, as you can see. The crypto components of these devices have been fully vetted and ready for the stringent environments for which they were designed to work in. And if you look at its key features, you can see it has a standard SPI interface supporting quad and octal. It has non-volatile monotonic counters, a true random number generator, physical unclonable functions or PUF support, hardware crypto engines. It supports symmetric and asymmetric key provisioning and management, and secure areas for authentication and encryption-decryption that can be configured, as well as standard areas can be configured for authentication. One thing I want to note here is that this part is highly configurable, so you can securely store data and also code in different partitions. Now with that, I'd like to return the presentation to Chris, who will give you a case example that they've encountered. So back to you, Chris.
Thanks for that, Jim. Let's now have a look at a design example where we can expand on all the functions and activities needed to ensure a secure product. Let's look at a smart building sensor gateway. This is quite a typical one. So here we've got a gateway which is connected to a multitude of sensors which are monitoring things like humidity, footfall, temperature, those kind of things. And the gateway is extracting all the information from the sensors and sending it to a server. The information needs to be secure. First of all, let's look at the function which is device provisioning. This is where you're actually going to take a bare metal device, such as a microcontroller or even your board, which is the computing heart of your product, and program security credentials into that device so that it can actually operate. The credentials, these can include software, cryptographic keys, and data, and they're typically programmed into secure memory in the device. In this case, it could be Armor Flash or the embedded flash in the device. The provisioning service can often be provided by the semiconductor manufacturer. So that is, the information is pre-provisioned into the device before it actually is delivered to the end customer. However, there are secure programming houses or even the end customer that could also provide this programming or provisioning service. Typically, the service must be carried out in a secure facility because you are handling secure information, and this ensures confidentiality of the credentials. However, there are technologies available that allow this phase to be carried out in an environment of zero trust, and this is an area where crypto Quantique can help you. Well, typically the device has now received a unique identity. This may have been created in several ways, either by injection of cryptographic keys or created from the actual DNA of the silicon itself. An example of this is a physical unclonable function, also known as a PUF. Now, these PUFs can provide a unique identity or a fingerprint of a semiconductor device. In the case of a PUF, the security is enhanced due to the fact that the private identity key, which is used to prove identity, never actually leaves the device. And here again, Crypto Quantique is able to help customers in this area. Provisioning will also ensure that certificates are included in the device memory. These are used as trust anchors and provide a chain of trust for the device to authenticate servers that it may be connected to. There may also be private cryptographic keys that you want to provision in the device. These obviously would need to be protected behind hardware secure barriers, which we have talked about, or firewalls, and these would be held in secure memory. Okay, let's now have a look at the next step in producing our sensor gateway. So now we have a semiconductor device that has been provisioned with credentials. We've just seen that. So how can we ensure that any software image is correctly programmed into the device? We do this by using the secure boot process, which we touched on earlier. This ensures that the gateway has an immutable boot process that cannot be interrupted and always checks the integrity and authenticity of the software image prior to actually executing it. Typically, a secure boot process uses either of two types of methodologies for software image verification. One is through the use of a hashing algorithm, and the other is through the use of a cryptographic signature. So let's have a look at each of these verification methods in a little bit more detail. The use of a hashing algorithm for verification is basically to check the integrity of the image that's been delivered to the device. So it ensures that none of the bits in the image have been tampered with and that the delivered software image is identical to the one that was sent to the device. Hashing does not really provide any authentication of the image, it simply shows that it hasn't been tampered with during transmission. The second methodology uses a cryptographic signature. Now, this is the methodology whereby the firmware image is delivered along with a signature. This signature includes a hash of the firmware image, but this hash is also encrypted. Now, the hash is encrypted using the private key of the owner of the software image that actually sent the software. The public key of this private key has been pre-provisioned into the device, which we mentioned earlier in provisioning. During the software boot process, the device decrypts the hash by using the public key that's been provisioned into the device and uses this to verify the hash against the firmware image. Once the process is complete, the device knows that the software image has been received and has not been tampered with, but also that it originated from the correct owner. Now that we have a device which has been pre-provisioned with credentials and we know it is executing software that is authentic, we can now begin to look at the connection of that device to the cloud service. So some examples of these cloud service providers are AWS, Microsoft's Azure, or Google Cloud. In order to connect to these cloud services, a public key infrastructure needs to be implemented. So this ensures that the digital certificates are in place to allow the setup of secure communications channels, which is what is needed by the providers. To connect to a cloud service provider, typically you need to initiate a secure connection. An example of this is TLS, or Transport Layer Security. It's a security protocol. Here we have a diagram of the interaction between a device and a server, which shows the steps involved in setting up a TLS connection. As you can see, the setting up of these connections is quite complex and requires the exchange of certificates and the generation of cryptographic keys in both the server and the device. During the setup of the connection, both the server and the device are required to authenticate each other, and this is done through the certificates, and this is where the unique identity comes to the fore. Now, this kind of connection is ideal for automation, and here is where Quantique can help you with the automation of onboarding a device to a cloud service provider. And finally, we look at the lifecycle management of the device. This is where we ensure the security of the device throughout its entire life while it's out in the field. Typically, lifecycle management utilizes certificates, which have validity periods and can also be revoked. But how does this actually help with the security of my device? Well, certificates can be used to control the connection of devices to cloud services, as we've seen. If a vulnerability is found in a device, it can be removed from that cloud service by revoking its certificate. Once a certificate has been revoked, that device can no longer make contact with the cloud service provider, and it can't set up a secure link because its certificate has been made invalid. With an invalid certificate, the device is unable to authenticate itself. Validity periods of certificates are useful because it ensures that owners keep on top of threat developments. If you had a certificate with 100 years validity, you would tend to leave that device in the field and not pay too much attention to any vulnerabilities. However, if you had a system in place whereby certificates had to be updated and refreshed, part of that process would be checking whether any vulnerabilities have been discovered and require repair. Also, cryptographic key rotation is typical to ensure that keys do not stagnate. The use of private keys to sign certificates could mean that if there are many certificates in the field, the private key has been overexposed and could become vulnerable. So rotating private keys ensures that attackers have a reduced period of time where they can attack the device to discover the identity of a private key. This is similar to the requirement to refresh your password, which is enforced by your IT department. So I hope that in this example you have seen many of the complex functions that are needed to ensure a secure connection of a device to a cloud service. These complex functions have been integrated into Quantique security platform. Our QuarkLink product is key to reducing the IoT scaling gap by providing customers with the automation of many of the functions covered in this presentation. So thank you very much for listening, and now I'd like to hand back to Jim to cover the summary of today's presentation.
Thanks again, Chris. I'd like to quickly summarize use cases Macronics sees as it relates to the whole IoT, IIoT segment, from data centers down to the end nodes. we're seeing rapid evolution in architectures. For example, compute domains, they're being distributed down into the customer premise domains, into edge devices and in nodes, really due to the latency and management of high amounts of data that are being generated. And then AI is playing a larger role in these edge devices and in nodes. Then, of course, connections to the untrusted public internets are increasing, and that's leading to a need for stronger security. And then that's really translates into rapidly changing memory requirements. So, for example, higher and wider range of density and types, adherence to different security standards like FIPS and ISO standards. And then secure provisioning and attestation support is required. And then increased security throughput for example, through the MCU, where authentication and encrypted connections are important. And then the need for larger densities to store secured information like services, features, applications, and credentials associated with that, as well as logs and management information. And then I've got a couple of examples up here in robotics and in servers and storage that you can see where we have parts designed in. So as you can see here in robotics, for example, we've had NOR flash, parallel 8 megabit NOR flash, and then over in servers and storage, you can see a wide range of NOR flash, NAND, and eMMC. I'd like to conclude our presentation by saying that we're in an exciting time in history with the acceleration of connected devices. It's creating new opportunities and economies of scale, helping us to better manage our society and do it more accurately. However, it's important that we think of security from all angles, from the beginning of a product design through its life cycle. And it must be thought of initially from what it is you're trying to protect. But even if you don't think the data that you're trying to protect is that important, think about how a bad actor might use security holes to get into servers or other parts of the internet to cause harm or theft. Lastly, to implement security into as many device interfaces as possible, including memory, where so much information is stored, is really important. And this is where Macronics can help with a highly configurable secure flash memory. And finally, I'd like to thank Chris and the Crypto Quantique team for a partnership we have to create a more secure computing environment. If you have any further interest, there's a white paper that goes a bit deeper into the secure memory architectures, and there's a link to Crypto Quantique's products and services. Thank you all for attending, and back over to you, Chris, for our Q&A session.
All right, well, thank you, Jim and Chris, for a great presentation. As a reminder, please fill out the feedback form that will open up at the end of the show. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you on programs in the future. We're going to now move on to the question and answer portion of our event. As a reminder, if you'd like to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or you can click on the Q&A icon at the bottom of your screen, type your question in, and then click the Submit button. Please note that we'll try to get to as many of your questions here as we can in the time that we have left. If we're unable to get to your individual question today, someone will get back to you after the program is over. So, gentlemen, we've got quite a few questions coming in. Our first one, what are the interface or other requirements to design Armor Flash in, and is there any IP or other functionality that needs to be in place?
Yeah, Chris, I can take that one. This is Jim from Macronics. So there is no a special IP that's required on the interface. It's just a standard SPI interface. And on the host side, the only thing that it requires is obviously the ability to do some of the crypto functions, and that can be done in software or it can be done in hardware. And, you know, obviously if it's in software, it's going to be slower. So oftentimes what we see is that it implements the hardware encryption engines. But other than that, it's a pretty standard connection. Thanks.
All right, thank you, Jim. And we'll move on to another question here for you gentlemen. What tools are available from the Crypto Quantique that can help with my connected product security?
Oh, thanks, Chris. I'll take that one. It's Chris here from Crypto. So one of the products we have is our QuarkLink security platform. What this is an agnostic software product. It's based on Kubernetes, so it can just fit in any Docker container, which means it can be installed on either the customer's server if they want to run it, or it can be installed anywhere in the cloud. What you can do with this tool is automate the onboarding process and manage the security of your connected devices throughout the lifetime of the product. The other cool thing is that QuarkLink will actually generate the public key infrastructure for you. It'll do that automatically. And it will also manage all the certificates and keys of your connected product throughout its life. So the idea of QuarkLink is to simplify security and provide customers with like a seamless security solution. So you don't need to get too involved in certificates and key management. It will handle that for you. So that's our QuarkLink product.
All right, thank you, Chris. We've got another question that's come in, and this one asks, what are the key differences between Armor 1 and Armor 2?
Yeah, Chris, I can answer that as well. So the key differences is in the density, but also in some of the configurability. The Armor 1 is a 256 megabit part, so it has a secure code storage area, as well as a data area that it securely stores data, but also a code area for just standard code accesses. So that partition is 224 megabits, and the secure data storage is 32 megabits. And that secure storage area is again highly configurable into partitions, and those partitions can be configured to be, standard SPI or various levels of security. And it's a single SPI interface. And then the Armor 2, our next generation, is much more configurable. It's a 64 megabit part, but the nice thing about that is that it can be configured for both code storage and secure data, again, in a very highly configurable way. And for the code storage, for the unsecure area, it can be a standard quad SPI interface, but also octal. So you can, enjoy just normal code accesses. Obviously, if an area is partitioned to be encrypted, it's going to have more latency associated with it, and that's, like I said, typical of storing secure data. Hopefully that answers your question.
All right, thank you, Jim. And our next question here asks, do you have any software to help support design in efforts?
Yep, I'll take that again. This is for Armor, and we do have a full library that you can take and adopt, and we support a number of different chipsets. And the software itself is a command library. It has the software drivers, as well as I say, the command library that handles all the commands, all the secure commands, as well as status and that sort of a thing. So, and we provide, the API to the crypto interface, depending on what crypto libraries you want to use, or whether or not you want to interface that to, hardware encryption engines. So we have a lot of support for these parts. Thanks.
All right, thank you, Jim. Our next question asks, how does my connected device communicate with a QuarkLink?
Okay, Chris, I'll take that one. Chris here from Crypto. So basically, once a QuarkLink has been installed, as I mentioned earlier, it's our software security platform. It can be contacted by the device that has been provisioned with the root certificate of that particular QuarkLink. So if you have a QuarkLink installed, it automatically configures itself and generates its own PKI, as I mentioned before, and at the top of that PKI is its root certificate. So you can access that at any time, and then the connected device, the IT device, actually will have that root certificate somewhere in its firmware. It will need that to actually initiate the communication and authenticate itself with the QuarkLink. And it will also, of course, require the URL of the quark link so that it can actually call out and communicate with it. Once the device is called out on the URL and it's got the root certificate, the quark link will set up a secure channel with that device. It'll actually set up a TLS 1.3 secure channel. This would have been pre-configured, and then the device will get sent all its credentials that it will need to onboard to its cloud service provider that has been configured into the quark link. So the device calls out the quark link, sets up a TLS connection, and then over that secure connection, the quark link sends down all the onboarding information to the device. So that's how the communication works. And then the communication is disconnected once that's done. Thanks.
All right, thank you, Chris. And we've got time for just a couple more questions here. Our next one, how do you protect the data while it's being processed?
Yeah, Chris, I can answer that one. So it depends on, when it's processed. I guess it's not data at rest. It's, it's data, I guess what process means being transferred. So the link can be encrypted. And in addition to the encrypted link, there's an authentication process that happens. So the part is authenticated with shared keys, with shared secrets. And then from that, there are a number of other factors that are built into the protocol that make it truly unique. And when the hashing is done and encrypted, it's done with these other factors in mind to create this truly unique signature. And so the data is then transferred back to the host or host to the device in a highly secure way. And all of this was tested at NIST to ensure that it met their qualifications. So we are CAFP qualified on the Armor 2 and on the Armor 1. Actually, the ARM PSA labs tested that one as well. So again, it's highly secure. Thank you.
All right, thank you, Jim. The next question here says, is Crypto Quantique's quark link compatible with Armor Flash?
Okay, I'll take that, Chris. So the great thing about our quark link product, the security platform, is it can utilize many different types of roots of trust. So these include puffs. If you have key injection into your product, maybe you've got an HSM on your manufacturing line to inject keys, and the quark link can interface with that type of root of trust, or even software roots of trust, various different types. The quark link basically requires an asymmetric key pair to be provisioned into the target device, because that's then used to actually prove the identity of the device. So the quark link basically goes through a challenge response sequence to make sure that the device actually owns the identity it has actually put forward. So Armor Flash can be utilized to protect these asymmetric keys, whether they're injected or generated internally by the processing system. So yes, it is compatible with Armor Flash. Thanks.
All right, thank you, Chris. And our time for our last question here. Our last one, what is the puff function?
Chris, I can answer it. It's a physical unclonable function, and what it is essentially is it's a digital signature, not signature. It's a digital ID. It's a unique, random, highly random number that's produced that can be used to uniquely identify our device. And so, the one thing I want to point out here is that it's based on a NOR cell function, so it has the same longevity that a NOR cell would have, as opposed to say SRAM, which in the past there have been problems with. So it's a number that is very durable. Or a design that's very durable. And there's a lot on the web you can find about it, but I just wanted to point out kind of the unique properties of our particular puff device. Thanks.
All right, thank you, Jim, and thank you, Chris. That's all the time that we have for our questions for today. Once again, I'd like to thank Jim and Chris for a great Q&A session and presentation. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. And once again, if we did not get to your individual questions, someone will be getting back to you after the program is over. Once again, we'd like to thank you for attending today's webinar, Securing Flash Memory in IoT and Edge Devices, brought to you by Tech Online and Macronics. And this webinar is copyright 2021 by AspenCore. The presentation materials are owned by or copyright by Tech Online and Macronics, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests and Macronics, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.